Alright, let's go. Number 10. WR-104 and the pinwheel aimed at us. In 1998, at the Keck Observatory in Hawaii, astronomer Peter Toutill of the University of Sydney pointed an aperture-masking interferometer at a faint Wolf-Rayet star roughly 8,000 light-years away in the constellation Sagittarius. He and his team weren't hunting for anything alarming. They were mapping the dust plumes produced when two massive stars orbit close enough that their stellar winds collide and condense. What came back, in the images published over the following years, was a structure too regular to look accidental, a tight spiral, wound like a fingerprint, glowing steadily in infrared light. They named the star WR-104. The established picture of Wolf-Rayet stars is straightforward. These are massive stars in the last violent phase of their lives, shedding their outer layers so fast that when the core finally collapses, the result is a core collapse supernova. In the rare cases where that collapsing core retains enough angular momentum, the explosion channels its energy into narrow, relativistic jets, instead of spreading it evenly in all directions a gamma-ray burst. The rule astrophysicists have relied on for decades is simple. A burst only matters to a distant observer if its jet happens to point almost exactly at them, within a few degrees. Everyone else just sees a bright new star, and nothing more. The spiral itself was the problem. A pinwheel-shaped dust plume like WR-104's forms in the orbital plane of the binary system, and that plane can be used to infer the orientation of the star's rotational poles, the same poles a gamma-ray jet would erupt from, if one ever fired. When Touthill's team modeled the geometry, the spiral came out looking almost face-on from Earth's perspective. With an estimated inclination of only about 16 degrees from our direct line of sight, that is close enough to the aimed-at-us zone that the story spread well past the astronomy journals. Later reanalysis of the interferometric data pushed the estimated inclination higher, toward 30 or even 45 degrees, which would swing any future jet's likely path away from Earth. But a higher estimate is not a settled one, and a companion star's gravity can torque a rotation axis over long timescales in ways current models still struggle to pin down precisely. The debate has not closed. Toutill and his collaborators continue monitoring the system as better instruments come online, and the community remains split on how heavily to weigh the original. More alarming alignment estimate against the newer, safer numbers. What isn't contested is the timeline. The core could collapse in a few 100,000 years, or considerably sooner, and nobody currently has a method to narrow that window any further. A gamma-ray burst travels at the speed of light. There is no early warning system for a beam that arrives at the same instant as its own light. If WR-104 is aimed even close to correctly, we would get no advance notice at all. We would simply be looking straight into the barrel on the day it fires. Number 9. Eta Carinae and the eruption that never really stopped. In the early 2000s, astronomer Nathan Smith of the University of Arizona turned the Hubble Space Telescope toward one of the most heavily studied objects in the southern sky, Eta Carinae, a stellar system roughly 7,500 light-years away, wrapped in a twin-lobed cloud of gas and dust known as the Homunculus Nebula. That nebula was ejected during the so-called Great Eruption of 1843. An event so violent, it briefly made Eta Carinae the second brightest star visible from Earth, without the star actually exploding. Smith's team wanted to understand what kind of star survives blowing off that much of itself and keeps on burning. The established framework for stars this massive treats an eruption of that scale as a late-stage event. Eta Carinae's primary component is estimated at somewhere north of 90 times the mass of the Sun, and the expectation for stars in that range has been that an outburst violent enough to eject a visible nebula should mark the final centuries of the star's life, with a supernova, or possibly something more extreme, a hypernova, capable of driving a gamma-ray burst following on a comparatively short and at least loosely predictable timeline. More than 180 years after the Great Eruption, Eta Carinae is still there, still unstable, and still not exploding. Spectroscopic monitoring has tracked its brightness and wind structure shifting on the timescale of years, rather than settling toward any clean end state. And the 5.5-year orbit of its companion star continues to generate shockwaves that X-ray observatories record in real time. Some models built from its current mass and instability estimate core collapse could arrive within a few thousand years. Others argue the system could persist considerably longer, shedding further mass in additional eruptions rather than collapsing on any schedule the current models can commit to. The one point researchers cite with something like relief is geometric. Inclination estimates suggest Earth is viewing the system nearly edge-on rather than down a rotational pole, which would make a directed gamma-ray burst far less likely to point our way, even if the star eventually produces one. The open debate now concerns mechanism and timing rather than outcome. Nearly every researcher studying the system agrees Eta Carinae will eventually end catastrophically. No consensus exists on whether that ending looks like an ordinary core collapse supernova, a hypernova, or something the 1843 eruption was only a preview of. Smith's group, along with several others, continues tracking the homunculus nebula's expansion for further clues. A star that massive does not fade quietly. It has already tried to end once, in full view of Earth, and reconsidered. It is still deciding. Number 8. Betelgeuse and the dimming that fooled an observatory. In the closing months of 2019, astronomer Edward Guinan of Villanova University, who had tracked the red supergiant Betelgeuse's brightness for decades as part of a long-running photometric survey, watched the star do something it had never done in the observational record. It dimmed by more than a full magnitude, dropping to roughly 36% of its normal brightness by February of 2020. Betelgeuse sits about 548 light-years away in Orion's shoulder, close enough and bright enough that the dimming was visible to the naked eye across much of the world, and public speculation moved faster than science. Was this it? Was the supernova finally happening? Live, in real time. The established understanding of red supergiants like Betelgeuse held that stars of this size with a radius on the order of 700 times the Sun's shed mass constantly through steady stellar winds, but do so gradually, without an unpredictable, sudden dimming of the kind visible to the unaided eye from Earth. If Betelgeuse really was showing genuine pre-collapse instability, it would represent the first time in recorded history that a star this close had put its final act on public, naked-eye display. It wasn't a supernova. A 2021 study led by Miguel Montargues of the Observatoire de Paris, using the European Southern Observatory's Very Large Telescope, found that Betelgeuse had ejected a massive plume of surface material that cooled into an opaque cloud of dust, drifting between the star and Earth, blocking a portion of its light. A stellar sneeze, in other words. Mistaken by a fair share of the internet for a death rattle. But the underlying question the Great Dimming reopened is a real one. Betelgeuse is in the final stage of nuclear fusion before core collapse, an event that could occur anywhere within the next 100,000 years in eye blink. In stellar terms, and current models cannot rule out further large-scale surface convulsions before the actual collapse arrives. What's settled is that Betelgeuse's eventual supernova poses no direct physical threat to Earth. 548 light-years sits comfortably outside any radiation kill radius researchers have modeled for an event like this. What isn't settled is how close the star's outer layers already are to genuine instability, and whether the Great Dimming was an isolated event or the first visible symptom of a star running out of time faster than the textbook models expected. Guinan continues his photometric monitoring. Montargues' team continues imaging the dust. When Betelgeuse finally goes, it will briefly outshine the full moon, and it will hurt no one. The star spent 2020 rehearsing its death in front of an audience that couldn't yet tell whether the curtain had already fallen. Number 7. Pegasi and the Nearest Bomb. Catalogued simply as HR 820, the binary system known as Pegasi sits about 154 light-years from Earth in the constellation Pegasus, close enough that amateur astronomers with modest telescopes can locate it without much difficulty. It draws attention not for its brightness but for its composition, an ordinary-looking A-type star locked in a tight orbit with a compact white dwarf companion. Pegasi b, that is already sitting close to one of the most consequential thresholds in stellar physics. The established rule governing white dwarfs is the Chandrasekhar limit. Roughly 1.4 times the mass of the Sun is the maximum a white dwarf can support against its own gravity using electron degeneracy pressure alone. Cross that limit, typically by pulling in material from a companion star, and the white dwarf doesn't simply collapse further. It detonates entirely, in a Type 1 supernova, one of the most luminous and best characterized explosion types astronomers study. Ik Pegasi b is already estimated to sit close to that limit, and its companion, Ik Pegasi a, is a main sequence star expected to evolve into a red giant within a few million years, expanding enough to begin transferring mass onto the white dwarf. If sufficient material crosses over, the white dwarf could be pushed past the Chandrasekhar threshold and detonate as a Type 1a supernova, which would make Ik Pegasi the closest known system to Earth with a specific, physically plausible mechanism for producing that particular kind of explosion. Several analyses have flagged the system for exactly this reason, since Type 1a supernovae are dramatically more energetic across a wider range of wavelengths than the eventual core collapse deaths expected from stars like Betelgeuse or Antares. Meaning the same kill radius math produces a larger danger zone for less distance. The counterweight researchers point to is time and motion. The mass transfer phase isn't expected for several million years, and over that span the system's proper motion through the galaxy will likely carry it considerably farther from Earth than its current distance. No firm consensus exists on precisely how much farther, because that depends on orbital dynamics that haven't yet been modeled with the precision the question deserves. For now, the nearest system with a working blueprint for detonation sits 154 light-years away, quietly running out a countdown that started before humans existed, and, according to the current numbers, won't finish until millions of years after we're gone. Number 6. Spica and the Twin Countdown. Visible as the brightest star in Virgo, Spica is in fact two stars orbiting so close together that ground-based telescopes cannot resolve them as separate points of light. Their binary nature was confirmed only through spectroscopic analysis of the shifting absorption lines in their combined light. A body of work stretching back over a century and refined more recently with modern interferometry. The system sits roughly 250 light-years from Earth. Massive stars and binary pairs are expected, under standard stellar evolution models, to live fast and die separately. The more massive star exhausts its core fuel first, collapses and detonates, typically leaving its companion intact, sometimes with a dramatically altered orbit as a result. That is the established sequence: one death, and then, independently and much later, the other. What makes Spica unusual is that both components are massive enough to end their lives as core collapse supernovae, the primary, at roughly 10 times the Sun's mass, the secondary at roughly 7, meaning the system isn't looking at one eventual explosion, but two, on staggered timescales separated by however many million years the smaller star's slower evolution buys it. Their tight, 12-day mutual orbit also distorts both stars into egg-like shapes under each other's gravity, a distortion measurable directly through periodic changes in the system's combined brightness. And that same close gravitational interaction raises open questions about whether mass transfer between the pair could accelerate or complicate either star's path toward eventual collapse. Researchers modeling massive binary evolution generally agree Spica's primary will detonate first, on a timescale of a few million years, but no firm consensus exists on exactly how the secondary's evolution, and any mass it gains in the process, will alter its own eventual death. At 250 light-years, neither explosion is expected to pose a direct hazard to Earth. Spica is not one dying star. It is two, orbiting each other every 12 days, each one waiting its turn. Number 5. Antares and the skin it cannot hold. In 2017, a team led by astronomer Kiichi Onaka, then working with the Max Planck Institute for Radio Astronomy alongside international collaborators, used the Very Large Telescope Interferometer in Chile to do something that had never been done for this particular star: map the motion of gas across its visible surface, cell by cell. The target was Antares, the red supergiant marking the heart of Scorpius, roughly 550 light-years from Earth. The standard model of a red supergiant's outer atmosphere treats it as governed primarily by radiation pressure, with a relatively smooth stellar wind-carrying material away in a gradual, mostly symmetric pattern, a picture consistent with what convection models had predicted for a star at this stage of its evolution. The velocity map Onaka's team produced showed something rougher. Turbulent gas motion that couldn't be explained by radiation pressure alone, moving at speeds and in patterns consistent with large convective cells, some individually comparable in scale to a planetary orbit, churning material outward with enough force to help explain how a star like Antares sheds so much mass before it dies. The findings suggested that existing one-dimensional models of red supergiant atmospheres are missing an entire dimension of turbulent motion, and it left open exactly how much of the star's eventual mass loss this convection accounts for, versus other processes still unmodeled. Antares is expected to end as a core collapse supernova at some point in the next several 100,000 to 1 million years, a timeline that remains approximate, because the internal physics governing exactly when a red supergiant this size exhausts its fusible core material is still an active area of stellar modeling research. No team currently claims a precise collapse date, and none likely will for some time. Antares cannot hold its own surface still. Something that large, that unstable, is not resting. It is shedding itself, one convective cell at a time, on the way to an ending nobody can currently schedule. Number 4. The kill zone no one has ever measured. In 2014, physicist Tzvi Piran of the Hebrew University of Jerusalem and astrophysicist Raúl Jiménez of the University of Barcelona published a study modeling how often a gamma-ray burst might occur close enough to a given planet, across the sweep of cosmic history, to threaten complex life. Their work, published in Physical Review Letters, wasn't about any single named star. It was about a distance, the question of exactly how close is too close. Earlier, less formal estimates of a gamma-ray burst kill zone had circulated for years, generally suggesting that a burst within a few thousand light-years, if beamed directly at a planet, could deposit enough gamma radiation to trigger widespread destruction of an ozone layer, exposing surface life to lethal ultraviolet radiation for months or years afterward. The expectation going into more rigorous modeling was that events like this should be exceedingly rare for any single location across the age of the galaxy. Piran and Jimenez's modeling estimated that a lethal gamma ray burst one close enough and well-aligned enough to cause serious biological damage on a planet like Earth has likely occurred somewhere within the Milky Way, roughly once every few 100 million years on average, and that earlier in the universe's history, when galaxies were more compact and more actively forming stars. The odds of any given galaxy's habitable planets being sterilized by such an event were considerably higher than they are today. The estimate implies that Earth shares its galaxy with a background hazard rate that is not zero and cannot currently be pinned down beyond an order of magnitude, since it depends on burst rates, beaming angles, and atmospheric shielding factors that are all independently uncertain. The concept of a kill zone radius remains a modeled estimate rather than a measured one. No gamma-ray burst has ever been observed close enough to test the boundary directly, and different research groups modeling ozone depletion, atmospheric chemistry, and burst beaming continue to arrive at somewhat different radii. What researchers do agree on is the shape of the risk. It is not zero. It is not evenly distributed across cosmic history, and it does not require an intelligent target to be devastating. There is a distance at which a star's death stops being astronomy and starts being a public health event. Nobody has ever agreed on exactly where that line sits. Nobody has ever needed to. Yet, number 3. The iron that fell from a star we never saw. In 2016, a team led by nuclear physicist Anton Wallner of the Australian National University published findings in the journal Nature describing an isotope of iron, iron-60, recovered from deep-sea sediment and crust samples collected at multiple sites across the Pacific, Atlantic, and Indian Oceans. Iron-60 does not occur naturally on Earth in any meaningful quantity. It is radioactive, with a half-life of roughly 2.6 million years, and any that existed when the planet formed should have decayed away completely billions of years ago. The established assumption about heavy radioactive isotopes like iron-60 is that they are forged almost exclusively in the extreme conditions of a supernova or a neutron star collision, and that finding measurable quantities embedded in terrestrial material would require the isotope to have arrived relatively recently, in geological terms, from somewhere outside the solar system. since no ordinary Earth process is capable of producing it in these quantities. Wallner's team found the iron-60 signal distributed globally, layered at specific sediment depths corresponding to two distinct time windows, roughly 2.6 million years ago, and an older, second pulse around 6 to 9 million years ago. The global spread and the sediment dating both pointed toward the same conclusion: the material arrived from outside the solar system, most likely as debris from one or more supernovae that exploded relatively close to Earth, probably from within a group of young massive stars known to have been passing through the solar neighborhood around those times. Subsequent research, including analysis of lunar soil samples and even Antarctic snow, found matching iron-60 signatures, reinforcing that the original finding wasn't a sampling artifact confined to ocean sediment. What remains unresolved is identification. No research group has definitively named the specific star or stars responsible, and estimates of how close the explosion needed to be to deposit this much material still carry meaningful uncertainty, generally clustering in the low hundreds of light years, distant enough to have caused no mass extinction on its own, but close enough that its physical debris is right now mixed into the floor of every ocean on Earth. A star exploded before humans existed, and pieces of it are still down there, in the mud, radioactively ticking toward zero. We didn't see it happen. We found the evidence in the ground beneath the water instead. Number 2. The extinction written in trilobite eyes. In 2004, physicist Adrian Melott of the University of Kansas, working with a team of collaborators, published a hypothesis in the International Journal of Astrobiology addressing one of paleontology's oldest unsolved mysteries, the end-Ordovician mass extinction, which killed an estimated 85% of marine species roughly 445 million years ago, at a time when nearly all complex life still lived in the ocean. Melott's team asked a question outside the usual boundaries of paleontological inquiry. What if the trigger wasn't volcanic, or glacial, or biological at all, but came from somewhere well outside the solar system? Mainstream extinction research at the time focused on Earth-bound mechanisms. A well-documented glaciation event and the associated drop in sea level were the leading suspects. Consistent with standard models of how mass extinctions unfold through climate disruption and habitat loss, both of which leave direct traces in the rock and fossil record. Melott's team pointed to a pattern the glaciation model didn't fully explain on its own. The extinction's severity correlated with ocean depth and geographic latitude in a way consistent with ozone layer collapse and a resulting spike in surface ultraviolet radiation, evidence for which came partly from shifts in the geographic distribution of trilobite species with differing light sensitivity, alongside a documented change in ocean plankton populations that some researchers argue preceded the glaciation itself rather than following it. Their modeling proposed that a gamma-ray burst within a few thousand light years, even one too old and too distant to be independently detected today, could strip away enough of the ozone layer to trigger a OOV-driven collapse of surface marine ecosystems, potentially setting off the glaciation as an atmospheric chemistry side effect rather than an independent cause in its own right. Critics have countered that the glaciation evidence alone is sufficient to explain the extinction pattern without invoking an unobservable cosmic trigger, and that no direct physical evidence of a burst, no isotopic signature comparable to the iron-60 findings from more recent events has ever been recovered from rock this old. The hypothesis remains contested, rather than confirmed. Melott and his collaborators have continued refining the ozone depletion modeling in subsequent papers, while other researchers maintain the extinction is fully explained by terrestrial glaciation and sea level change alone. No consensus has emerged, and because isotopic evidence has never been recovered for an event this old, none may ever be reachable through current geological methods. Somewhere 445 million years ago, something may have gone off in the sky, and 85% of everything alive in the ocean may have died because of it. We may never be able to prove which. Number 1. The fire that already touched us. In a series of papers spanning more than a decade, physicist Brian Thomas of Washburn University, frequently working alongside Adrian Melott, has tried to answer a broader version of the question the Ordovician hypothesis first raised. Not whether one burst struck Earth once, But how many times something like it has probably happened across the entire 540 million year span of complex life on this planet? And how many more times it is likely to happen before that span eventually ends? The established statistical picture of the Milky Way holds that core collapse supernovae occur somewhere in the galaxy roughly once every 50 years on average, that only a small fraction occur close enough to Earth to matter biologically, and that gamma-ray bursts capable of a direct hit are considerably rarer still, though individually far more devastating when properly aimed. Standard models have generally treated events like this as background noise statistically real, but rare enough at any single location that no observer should reasonably expect to experience one within a human lifetime. Or even across the whole of recorded history. Run the numbers over geological rather than human timescales, and the picture changes. Thomas and Mellett's modeling, combined with the physical evidence already recovered, doesn't leave this as a purely hypothetical exercise. The iron 60 in the ocean floor confirms at least 2 nearby supernovae within roughly the last 10 million years. The end Ordovician case remains contested, but unresolved rather than dismissed. Taken together, the evidence suggests Earth's surface has likely been irradiated by nearby stellar death more than once across the span of complex life, at intervals current estimates place anywhere from tens to hundreds of millions of years apart, a range wide enough to admit that the next interval could already be more than halfway elapsed, or could be nowhere close to starting. And no one currently has a method to determine which. What remains genuinely unresolved is not whether this happens. The iron 60 alone settles that question. What's unresolved is the size of the actual gap between events, and whether the specific ecological damage attributed to any single ancient extinction can ever be tied definitively to a cosmic rather than a terrestrial cause. Thomas has continued extending the statistical modeling to other extinction boundaries in the fossil record, without so far finding a second isotopic signature as clean as the one already sitting in the ocean floor. The iron from an exploded star is already inside the ground you are standing on. The mechanism that may have ended 85% of ocean life once has never been ruled out from happening again. Every model agrees on the shape of the risk and disagrees only on the clock. We are not waiting to find out if the sky can reach us. It already has. We are only waiting to find out if it's due. If you want to see more videos like this, click the video on screen now and make sure to subscribe.